All right, welcome back for day 2 of finite. If this is your first day in the class, I would make sure to watch our lecture video from the first day of class. That way you can kind of catch up on everything that I mentioned there. All right. So today we're gonna pick up where we left off last time. I'm gonna try to remember to do this every class period. If I ever forget, please feel free to call me out on it. But today, or really kind of by the end of today, we're going to cover 1 through 35 in homework number 1. So these are the questions I recommend doing by next Tuesday, or before next Tuesday. Because next Tuesday, we will then have another set of questions to work on. So the homework, if you have looked in my lab, there it is. If you look at my lab, you'll see that the homework is due September 16th, and that is true. That is when the homework is due. However, you need to complete certain portions of it to open the quizzes. So next week's quiz, you need to have completed most of 1 through 35. I think if you miss 1 or 2 of those, you still have enough. I don't remember the exact percentage, but you need to have worked most of 1 through 35. You need to have gotten through 40% of the homework to be able to open that quiz. So here's how I would recommend doing that, because here's what a lot of people do. They will wait until next week. They will not do any homework until next maybe Thursday. And then they'll do their homework on Thursday, and then they'll take the quiz on Friday. And that's fine, but that means you're also behind on next week's homework. So then the following week, you're trying to catch up on homework. And then you're just going to be a week behind for the rest of the semester. So I don't recommend doing it. I would recommend doing 1 through 35 this week. If that's this week's homework, do next week's homework next week, and so forth and so on. So a lot of people wait until the day of the quiz. Not the greatest way to do it. So anyway, all right. So let's jump back into linear systems of equations. I'm going to write down the one we did on Tuesday. You don't have to rewrite this one if you were here. We had x minus 2y equals 1 and 2x minus y equals 5. We were able to solve that and get that x was 3 and y was 1. We solved that a couple different ways, but the main way that we'll be using is the matrix way. If you remember, after we solved that matrix, it looked like 1, 0, 3, 0, 1, 1. And we were able to take that matrix and write out the equations x equals 3 and y equals 1 from them. It's this first one that is 1x plus 0y equals 3, or just x equals 3. 0x plus 1y equals 1, or y equals 1. Reminder, that looked like was about something like that. This type of solution, we say has one solution. Because there is exactly one x and y value that is shared by both of those linear equations. That is not the only possibility, but that is one possibility, that they cross exactly once. So what we're going to look at now are other possible types of solutions. All right, so let's look at another system. Let's look at negative x plus 2y equals 3 and 2x minus 4y equals negative 6. Do the exact same thing we did last time, which is we'll set up a matrix where, again, the first column are going to be the coefficients of the x's, second column coefficients of the y's, and then last column are our constants. I mentioned this last time, we do always need the equations in standard form to be able to put them into the matrix. We'll see an example here in just a little bit where it's not in standard form and we have to use some algebra to get it into standard form, and then we can complete the problem by using the calculator. Anyway, these are both in standard form. Standard form just meaning x's and y's on one side, constants on the other side. So coefficient for the x is -1, coefficient for the y is 2, and then our constant is 3 for our first equation. Second equation, we've got a coefficient of 2 for the x, -4 for the y, and -6 for the x. Reminder, we draw a vertical line there to represent where the equal sign is. Our calculator doesn't have that, but I would always recommend writing it out. All right. Now, if you're new to this class, I might be going through this part a little too quickly, but it was in our lecture video from Tuesday, and you can also see it in the pre-class assignment videos. So anyway, we want to put the matrix in, so we'll go second matrix over to edit. This is a 2x3 matrix, just like the one we dealt with on Tuesday. We've got -1, 2, and 3, and then 2, -4, 6. As a reminder, if you get an error message when typing numbers in, more than likely you accidentally use the minus button instead of the negative button. So just make sure you're using the negative button when typing numbers in. All right, so we'll quit out of that screen, and then we go back into the matrix menu. Second matrix, over to math, and then up to RREF. As a reminder, RREF is reduced row echelon form. It is a simplified version of the matrix. You don't have to know what it means, but as long as you know that it simplifies our matrices, that's enough. It simplifies them by the process known as Gauss-Jordan. That's a phrase you will see on some of the homework problems. So just FYI, see Gauss-Jordan, that means use the calculator to reduce your matrix. All right, so then second matrix, say, and we can just press it. So that is our reduced matrix. Yes.
So when you put in the original matrix, instead of -6, you put 6.
Oh, did I? It. Right, that makes a big difference. Thank you.
Yep.
Yeah, feel free to call me out on any mistakes, because that's going to be important. That would have changed. The problem. All right. Back to our There we go. That looks better. Oddly enough, the first thing is actually going to be our next example, so that's okay. So the 1, -2, -3, that's correct for our current example. So let's write that down. 1, -2, -3, and then 0, 0, 0. So just like our last problem, we're going to write these out as equations. I will tell you, one of the mistakes that I see most common on this test, out of everything we're going to talk about on first time, one of the mistakes I see most commonly is when people try to go from this right here, from this matrix, straight to typing their answer into MyLab. It is very easy to make mistakes if you do it that. So always take your matrix, write out the equations. You will get to where you don't need to do that for this type when there is one solution. And you'll kind of figure out the pattern of what one solution looks like. It's going to be 1s in the diagonal there, 0s everywhere else. But when you have anything that doesn't look like that, always write out the equations. So we're going to write those out. That would be 1x minus 2y equals -3. So that's our first equation. Our second equation is 0x plus 0y equals 0. Or just 0 equals 0. 0x plus 0y is just 0. Now, that is a true statement. 0 does indeed equal 0, but it's not giving us any information that is helpful in solving this problem. So really, we're left with just that first equation. And when something like that happens, we say that it has infinitely many solutions.
Because of the 0?
Not just because of the zeros. That's a good question, though, because that is how a lot of people memorize. So I'm going to write down here in just a second how we know for sure. So I will say, most of the time, when you have a row of zeros at the bottom, that means there's infinitely many solutions. But that is not always the case, so we don't want to count. So we know for sure if there are infinitely many solutions if the number of variables, that's your x's, y's, and z's. In this case, we have x and y. If the number of variables is greater than the number of unique equations. So I'll show you an example here in just a minute where we don't have a row of zeros and we still have infinitely many solutions. But this always will tell you we have more variables than unique solutions. So the unique part of the unique solutions is important because it's not number of variables is greater than the number of equations. Because we started off with 2 equations and we started off with 2 variables. So that seems like they match. However, if we look at our first 2 equations, specifically the second one, you'll notice that that second equation is just the first equation times -2. So it's not actually a different equation. It looks different, but mathematically it is the exact same thing, right? We can multiply both sides of an equation by a real number, and it doesn't mathematically change the equation, right? So that's really just the same equation written twice. And our RREF figured that out for us. That's why we ended up with 0 equals 0 down there at the bottom, is because that second row was redundant information. It wasn't unique, and so RREF just kind of canceled it out for us. So we really only have one equation, this one, where we have 2 variables, x and y. So when that happens, it's always infinitely many solutions. Now, what we're going to do, we're not quite done with this problem yet. To be able to solve this one, we want to know the general solution for the problem. To find the general solution, we're going to solve our equation in terms of whatever the last variable is. So if we have x and y is our last variable. We have x, y, z, z is going to be our last variable. It'll probably make sense on our next example why we do it that way. But anyway, so we want to solve for x in terms of y, which really just means adding 2y to both sides of that equation. Started with x minus 2y equals -3. Now add 2y to both sides. And I'll get x equals 2y minus 3, or -3 plus 2y. My lab doesn't care about the order of that. And so now I can write this as an ordered pair. So my x is 2y minus 3, and my y is 1. So now I have both variables, x and y, in terms of the same thing, which is 1. Okay, so notice I don't have any x's left, which just tells us that if I pick any y value, I can figure out what an x value is that is on this line. Which, by the way, if we were to draw this, the reason why we end up with infinitely many solutions is because if mathematically they're equivalent, then mathematically they're the same line. So really, I'm just drawing one line on top of the other line. So it's really just one unique equation. But what that means is that every single point on that line is a solution, because every point on that line is in common between both of those equations, because again, they're the same equation. So what we can do is we can find specific solutions. Using that general solution, we can find specific solutions. So for example, I could plug in, let's say 4 for y. So if I plug in 4 for y, then I would also plug 4 in for y there. And I have 2 times 4 is 8 minus 3. I would have 8 minus 3, which is 5. And so 5, 4 should be, I don't know where it is, maybe it's that one, should be a point on my line. Yes.
Sorry, for the 4, you were just plugging in a random.
Yeah, I just randomly picked a number. Yeah, you can pick it. In the homework, they will give you some example numbers and you will have to test to see if it's a specific solution or not. So maybe they'll give you like, I don't know, 16, 5. And we can test to see if that's a point on this line by saying, okay, well, if 5s are y, then I would have to do 2 times 5 minus 3. I would get that that's 7, 5 as a point, so 16, 5, definitely not a specific. So that's how the homework has to deal with those. It's like multiple choice. They'll give you like 4 of them or something and say which one of these is a specific solution. And you just plug the y value into both of them and see which one happens to y. So that's infinitely many solutions. First one we looked at was one solution, lines crossed at a single point. Infinitely many solutions, it's 2 lines that are right on top of one another. Again, we'll have infinitely many solutions. We have more variables than we have unique equations. Okay? So let's look at another example. I'm not going to work this one all the way through, but let's pretend we've got a matrix that is a 2x4 matrix. And we're going to say, we're going to do RREF on whatever this matrix is. I'm just going to make it up. I'm going to call it matrix A. And what we get is 1, 0, 1/2, 4, and 0, 1, 2, -1. So this is again after we have reduced. So we've already put the matrix in, we've reduced it. This is what we're left with. So notice here that we have 3 columns and then the constant column, which means we have 3 variables here. And how many unique equations do we have? Just 2, right? So notice there's no row of zeros here. We just started off with more equations than variables. The RREF process didn't eliminate one of our equations. We just started off with less equations. So looking at this problem, before you did anything on this problem, which this problem is in the homework, there's a couple of them like it. If you see that there's 2 equations and 3 variables, you automatically know your answer is going to be infinitely many solutions. Anyway, so let's go ahead and write these equations out, and that way we can find our general solution. By the way, usually what MyLab will do, or MyLab, what the calculator will do, is it will give you the answer as a decimal. There is, if you press the math button, it's right here, math. So right there, 3 buttons down on the left-hand side, and then select fraction right there. It'll change whatever your answers are from decimals to fractions, and that was pretty helpful. So if I did that here, it would change my 0.5 to 1/2. Typically, MyLab is going to want fractions as opposed to decimals, but if it wants decimals, it will tell you how many places to round to. Anyway, let's go ahead and write these out. So that is 1x plus 0y, so we can leave that off because that's just plus 0, plus 1/2 z equals 4. And in the bottom row, we have 0x, so we can leave that off, 1y plus 2z equals -1. So the way the Gauss-Jordan process works is it simplifies our columns as we go. So it simplifies the x one, simplifies the y, then simplifies the z if it can. In this case, it couldn't, because there's infinitely many solutions. Well, it could simplify it. It got it as simplified as possible, but it didn't find the solution because there isn't one. But because of that, that's why we always end up with all of our equations in terms of the last variable, because that's the last one that would get simplified. So here we notice that our 2 equations have z in common. So for both of these, we're going to be solving for x and y in terms of z. So for this top equation, I'm going to subtract 1/2 x from both sides. Or sorry, 1/2 z. X equals 4 minus 1/2 z. Same thing with the second equation, only we'll subtract 2z from both sides. So we get y equals -1 minus 2z. And so now we have all of our variables solved in terms of z. We know what x is in terms of z. We know what y is in terms of z. And z in terms of z is just z. So we've got our answer would be 4 minus 1/2 z. -1 minus 2z. And then, so that would be our general solution. So in your general solution, there should always only be one variable. Notice here it's z. In our previous example, it was a y, because again, that was our last variable. Always be in terms of one variable. Because that way we can just put a number in here if we wanted to find a specific solution. Let's say z is 5. Plug 5 in there and 5 in there and 5 in there, and then we'd simplify those two, and we'd have our specifics. All right. Any questions there? All right. Let's do one more to look at the one remaining type of solution. So we're going to actually take this exact same system, only we're going to make this last number a positive 6 instead of a negative 6. I did it on accident last time. We're going to do it on purpose this time. So we had negative x plus 2y equals 3. And then we're going to do 2x minus 4y equals positive 6. So that way we only have one number to change on our matrix A. Everything else will be the same. So we're just got -1, 2, and 3, 2, -4, and positive 6. All we have to do is go edit our matrix A. And this time we're going to make that last number at the bottom right, that -6, we're going to make it a positive 6. So, only thing we're changing. All right, same thing back to the matrix menu. We're going to do RREF to simplify our matrix. And we already saw that answer because I accidentally did this the first time. We have 1, -2, 0, 0, 0. Which we can notice definitely still looks different than our one solution problem, this one, which just had 1s and 0s over here on the left hand side, 1, 0, 0, 1. Here we've got something different, but same thing. We want to write those that matrix out as equations. Again, first column are x coefficients, second column are our y coefficients. So we have 1x minus 2y equals 0. Then for our second row, we have 0x plus 0y, so that's just 0, equals 1. And we, of course, know that is not true, right? 0 can never equal 1. It's never a true statement. And so what that tells us is that this system, very good, has no solution. Possible to have a solution when you have a false statement.
The 0 we did before did how many solutions?
Infinitely many.
Okay.
Yeah. Because we had more equations than variables, or more variables than unique equations. Yeah. So those are our three types of solutions that are possible. One solution, so you'll have an x and a y, or an x and y and a z, or however many variables you have. Infinitely many solutions, we'll come up with a general solution that'll be in terms of whatever the last variable is. And then we have no solution, which you don't have to do any more work once you figure out it's no solution, there's no more work to be done. But I do frequently have people mix up no solution and infinitely many solutions on the test. Easiest way to avoid that is just write out your equations. Once you see that 0 equals 1, it should be fairly obvious that that doesn't match correctly, and that must mean that there's no possible way. By the way, what I did by changing that number from a -6 to a +6 was I took those two lines that were on top of each other, right, our infinitely many solutions. I didn't change the slope, I just changed the y-intercept. Rather than them being right on top of one another, now they're exactly parallel. So that's why there's no solution, because parallel lines never cross. So those are the three things that can happen with straight lines. Is they can cross once, they can be the same line, cross infinitely many times, or they're parallel and they never. All right. Right. Okay. Yeah.
On the quizzes and tests, we have like scratch paper that gets turned in.
Yeah, so when you, so only the first quiz, because that's the only one you take in the testing center, but yeah. So when you test in the testing center, whether you're taking a quiz or a test, they will start you off with a blue sheet of paper. Each class has our own color-coded thing, so we can find them easier. The finite is blue. Up at the top, it'll have you put your name, your student ID number, yada, yada. And then you use the rest of it for scratch paper, and if you need more, they'll bring you more. Yeah.
What testing center?
It's Champions Hall.
Okay.
Yeah. Any other questions? All right. So now that we know the basics of systems of equations, now we can move on to the fun stuff. Word problems. I know, everyone's favorite. As I mentioned, the hard part of this class is not the math. The calculator does a lot of the math for us. The hard part here is going to be setting up the system and then interpreting the answers. So this question that I'm about to do, by the way, I stole right from the homework. So if you don't normally take notes, good one to take notes on, since you'll have to do this problem again. All right, so we have this company called UDrive. And they plan to spend $7 million on 200 new vehicles. They're going to buy some vans, which cost $35,000 each. Some small trucks, which cost $30,000 each. And some large trucks, which cost $50,000. They also want twice as many vans as small trucks. That's the part people have probably the most trouble with on this problem. So that's why we're doing it. Question tells us that we want to know how many each type of vehicle should they purchase. Second, finish writing that down. Now, I try when I design this class to make problems as realistic as possible. Sometimes that's not entirely possible. Is it possible that there's a company that wants to buy 200 new vehicles? Sure, maybe that's what they've got space for. Maybe that's how many drivers they've got. Maybe that's how many they think they can rent out. I don't know, but that is possible. Is it possible they need twice as many vans as small trucks? Sure, maybe that's twice as popular for renting out the vehicles or whatever. That's also fine. But as part of this problem, they have to spend exactly $7 million. And that's not really realistic. More than likely, they would either have a budget of $7 million, and if they could get the car cheaper, great. Or maybe they need to spend at least $7 million because, I don't know, they have a grant or they, need some sort of tax break or something. Anyway, we will get there. What we're gonna do the week after next is we'll start working with inequalities. So then we could have a budget of $7 million and what, how many of each type of vehicle fit best and keep us under our $7 million cap. So we'll get to those problems, but we have to start out here. So anyway, one of the things I've noticed in many years of teaching is that I don't think high schools do a great job of preparing people to solve word problems. So we're gonna take a step back before we solve this one, and we're gonna write out some steps for solving word problems. So I would either move farther down on your page or maybe move to the next page, give yourself some room for us to solve this here and then write these steps somewhere else. We're gonna write steps for setting up and solving word problems. These steps will be helpful both when we're working with equations like today and when we're working with inequalities like we will be in 2 weeks. Both of them have the same basic setup process. The solving process will actually be a little bit different, but the setup process will be essentially the same. All right, so step number 1. Identify your variables with units. I'll explain what that means. So one of the things I often see is that people will just start using X's, Y's, and Z's without actually knowing what they mean. And then they solve the problem and they get X equals 5, but they have no idea what that means because they didn't know what X was in the first place. And that, on some problems, sure, you can get away with it. It's not my recommendation, but you can get away with it sometimes. But on many, many other problems, you're not going to be able to get away with just using X's and Y's without knowing what they are. So we want to know what our variables are, and we want to know what the units for those variables are. Let's go back up to our problem. At some point in every problem, they're going to tell you what it is you're trying to find. Frequently, that statement will end with a question mark, because those are the things we are trying to find. So in this problem, we look for the question mark, says how many of each type of vehicle should they purchase? So we don't need a variable for the cost of the trucks. We don't need a variable for, gas mileage of the trucks or whatever else. We only need variables for how many. It's the only thing we're trying to figure out. So let's let X equal the number of vans. Don't just write X equals vans, because that is leaving off the units, and that can be confusing because you don't actually know what you're solving for. Because let's say we got 5 for X, then we have the sentence 5 is van, and that doesn't make any sense, right? We have 5 is the number of vans, that makes sense. Or 5 is the number of doors on the van, that could make sense. But 5 is van does not make sense. So we want to make sure we have units. Number of vans. Y, let's let that be the number of small trucks. And then let's let Z be the number of large trucks. You could use different variables if you wanted to, B, S, and T for van, small, and large. Doesn't matter. I like X, Y, and Z, but use whatever you like. Those are our variables. Those are the things we don't know. Just a reminder, variables are things we do not know. A lot of times students will choose things to be variables of numbers they already know. Make sure not to do that. Things we do not know. All right, let's go back down to our steps. Step number 2 is that we're going to write our equations starting with the totals. But what I mean by totals is the right-hand side numbers. It's probably backwards of how you're used to doing it. Probably backwards of how you want to do it. I promise it is easier and you will make fewer mistakes this way. There are not methods in this class that I teach just for funsies. Every method I teach you is because I think it is the best, easiest, most likely to get you to the right answer, least likely to confuse you. So, do you have to follow these 2 steps? No. Will you make less mistakes if you follow these 2 steps? I am confident that is true. All right. So, rather than starting off with something x plus something y equals something, we're going to start off with the something on the right-hand side and then go backwards. So, looking at the numbers that we have on this problem, what's one that looks like a total? 200 new vehicles, good. What else? The 7 million, right? We got a total of $7 million we want to spend, total of 200 vehicles we want to purchase, right? So typically 2 of the bigger numbers on our problem. All right, so let's do equals 7 million. And I'm going to write dollars after that. I would recommend doing the same. And then we'll do the same thing with the 200. That is vehicles. The reason why I do it this way is because now, see my 7 million, I see dollars. Because I have dollars on the right-hand side of my equation, everything on the left-hand side needs to be dollars. So I don't even really have to think that much about what goes on the left-hand side. I know it's just dollar. Here I know everything on the left-hand side is going to be vehicle numbers. Don't need any dollar numbers there. That's not what that's about. So starting with the right-hand side, you get to start with one number that's going to inform all of the other numbers. Whereas if you start on the left-hand side, you have to think about each individual one, and that can sometimes be confusing. We also want to make sure every single number in our equation refers to the same type of thing. So for this dollars one, we're going to start off with the vans. Those are $35,000 each. And that $35,000 is a rate, right? It's not the cost of all the vans we want to purchase. It's the cost per van, right? So we would take that cost and we'd multiply it by how many vans we're going to purchase. Right? Want to buy 2 vans, it's $70,000. 3 vans is $105,000, and so forth and so on. So we're going to do 35,000 times X, which is our number of vans. 35,000X gives us the total amount spent on vans. For the small trucks, those are $30,000 each. 30,000 times the number of vans, or sorry, small trucks. 30,000Y tells us the total spent on small trucks. And then we'll do our 50,000 for the large trucks. Again, that is also a rate, so it's going to be multiplied by the number of large trucks that we're purchasing. So 50,000. See, notice all of those numbers: the 35,000, the 30,000, the 50,000, the 7 million. All of those are dollars, right? There's a question in the homework where if you're not paying close attention and you're just grabbing the first number and putting an X after it, second number Y, third number Z, it's a problem about a company that makes these bagged vegetable mixes, and there's like broccoli and carrots and zucchini, I think, or something like that. And so very frequently I'll have someone email me, and what their equations say is take some broccoli, add some carrots, add some zucchini, and that equals carrots. That doesn't make any sense. Can't put 3 types of vegetables in a bowl and all of a sudden all of them be carrots. So you would want to do carrot number plus carrot number plus carrot number equals total number of carrots. Just like we did dollars plus dollars plus dollars equals dollars. All right, now our vehicle numbers. Notice that we're just looking at number of vehicles. So there's actually no rates here. We're not purchasing number of vehicles per week. Vehicles per year, we're just wanting to buy vehicles. There's actually no numbers in front of our variables. Our variables are already a number of vehicles, right? So we just have the number of vans plus the number of small trucks plus the number of large trucks needs to be 200. Again, no need for money numbers there because that's our vehicle equation. Got our dollars equation, got our vehicles. Now, we could have incorporated that they want twice as many vans as small trucks. We could have incorporated that into that second equation. So if you were thinking that, good job, that's smart. If you weren't, that's okay. But if we did it that way, we would have to solve the whole thing by hand and we couldn't use the calculator. We're not going to do it that way because we want to use the calculator. So instead, we're going to create a new equation that relates these two variables. Now, this type of equation isn't going to fit in my nice steps because not every type of problem has something like this. Usually, we have a total and we have something in relation to that total. What we have underlined in red there is a relation of one variable to another variable. And anytime we're relating two variables, that means they're going to be on opposite sides of the equal sign. So let's go ahead and actually just start there. X for vans, we're relating vans and small trucks, and then we'll also have Y, and we know there's going to be an equal sign in between them. What we're starting off with there is the number of vans is the same as the number of trucks, right? Which isn't true. But at least it's a good starting point for us to figure out what to do here. So it says they want twice as many vans as small trucks. So here is what most people want to do on this problem. And that is multiply the number of vans by 2. Which makes sense, right? If you want double the number of vans, it makes sense to multiply the number of vans times 2. Actually, not quite how mathematical equations work, though. Because really what we've done there is actually doubled the number of small trucks. Because when we read an equation, we start with the thing that's by itself. This is really just a sentence. And that sentence says the number of small trucks is double the number of vans. Right? So this is actually saying the small trucks is double the size of the vans. Right? We can see that mathematically if we just try putting something in. Right? Because I know if we want twice as many vans, let's say I wanted to buy 5 small trucks, I know that means I should buy 10 vans, right? So does that work? 10 vans, 5 small trucks? Nope, doesn't work. Instead, what it should actually be is we're saying the number of vans, which is X by itself, needs to be 2 times that of the small trucks. I know it seems like we're doubling the wrong thing, but really it's the wording of the sentence. Because if I worded the sentence to say the number of vans should be double the number of small trucks, you would probably get it right. So you have to really think about it because the wording of the sentence isn't necessarily going to give it all away. We want to make sure that the sentence or the equation makes sense. Here this is, again, number of vans is double the number of small trucks or is 2 times the number of small. And now if we try my example, where if I have 5 small trucks, we can see that that math does work out. All right. So we have our third equation is x equals 2y. But as a reminder, everything has to be in standard form for us to be able to use the matrix. So we need to subtract that 2y over. So I'm going to do that right above here. So I'm going to subtract 2y over. So I'm going to get x minus 2y. And then if I subtract 2y from the right-hand side, I just get 0. So those are going to be our 3 equations. We do always want to make sure that our variables line up. So that all the x's in the first column, all the y's in the second column, z's in the third. So when I subtract the 2y over, I don't want to put it in front of my x. It needs to go behind my x just so they're in order. There's no z on that last equation, so we're just going to put a 0 where that goes in our calculator. Okay, actually, so before we do that, let's go down to our steps. Ready for the next step? The next two steps are pretty easy. Steps 1 and 2 are by far the hardest two steps. Step 3 is put system into a matrix. Step 4, REF to solve. I'll just go ahead and write both of those now. Once we get our answer, then we'll be able to see, do we have one solution? Or are there infinitely many solutions? Maybe there's lots of different possibilities for the number of trucks and vans we could buy. Or maybe there's no solution. Maybe there's no way to spend exactly $7 million to get all of that stuff. But we're gonna find out. All right, so our matrix would be 35,000, 30,000, 50,000, 7 million. Second row would be 1, 1, 1, 200. And the third row, 1, -2 for y, 0 for z, and then equals 0. Again, we subtracted 2y from both sides, so that puts with 0 on the right-hand side of our equation. Got it into a matrix. Now we just want to put it into a matrix in the calculator. So we're going to use matrix A. This one is a 3x4 matrix. 35,000, 30,000, and 50,000. Total of $7 million. You'll notice when you type in that 7 million, it's going to change to 7E6. That E there is scientific notation. You'll see that sometimes when we work with really big numbers on the calculator. We got 1, 1, 1, 200 for the second row. And then 1, -2, 0, 0. All right. Quit out of there. Matrix menu up to RREF. You're gonna get really good at RREF by the end of this. You're gonna use it quite a bit. All right, there we got our answer. We can see just by looking at it that it is going to have exactly one solution. To the left of the right-hand column is our constants. To the left of that, we've got a diagonal of 1s, everywhere else 0. That's what it should always look like if we've got one solution. Let's go ahead and write that out. 1, 0, 0, 120, 0, 1, 0, 60, and 0, 0, 1, 1. The one solution ones are easy enough to just read from the matrix. Again, I would always write out the equations when you're dealing with infinitely many solutions and no solutions, because those are a lot easier to mess up. The one solution ones are much more challenging to mess up. So this one, we've got x, y, and z. So that first equation is 1x plus 0y plus 0z, or in other words, just x equals 120. Second row, 0x, 1y, 0z is just y, and then 60. And then 0x plus 0y plus 1z, or just z.
Does it matter what way you put the equations in for the rows?
It does not. Yeah, good question. So you can put the rows in any order. You'll always get the same answer.
How do you notice you want solution?
So the question was, how can you tell it's one solution? Anytime we end up with something that looks like this, where we have a diagonal of 1s there, 0s everywhere else, that's always going to be one solution. As a reminder, no solution, you're always gonna end up with zeros on the left and then a one. And then infinitely many solutions, well, infinitely many solutions can look different ways, but you'll always end up with more variables than equations. Here we have three variables, x, y, and z, and we do have three equations. So we end up with one. Now, we need to be able to interpret this, so it's good that we wrote out what each of those were. X was the number of vans, Y was the number of small trucks, Z was the number of large trucks. I know that seems really easy. You're gonna get some homework problems where that is more challenging, maybe than you expect. So anyway, we have 120 vans that we're purchasing, 60 small trucks, 20 large trucks. Did we purchase double the number of small trucks and vans? Yeah. Did we purchase 200 total vehicles? Yeah, do that in our head as well. Figuring out the money number one is not as easy in your head, but we could figure it out. We could multiply 120 times 30,000, 35,000, 60 times 30,000, and 20 times 50,000. And we could see that we did indeed spend $7 million. So the good thing about these word problems is you can double check your answer. We can know that we got it right before submitting the answer. And in fact, even if you had accidentally done, there where we had x equals 2y, if you had instead done 2x equals y, as long as you're paying attention to what your answer is, you could see, oh, I doubled the wrong thing, and you could go back and fix it. All right, any questions on that? Okay. All right, we're gonna change gears just a little bit. I know you saw most of this on the pre-class assignment. But we're gonna go over just a little bit of it. We'll be able to get through it in the next 15 minutes. So what we're gonna talk about real quick are matrix operations. We've used matrices, but we haven't learned a whole lot about them yet, other than we can shove a system of equations in there and have the calculator reduce it for us. Matrix operations are somewhat like real number operations, only they don't work exactly the same. We have similar ones. We have addition, we have subtraction, we have multiplication. We do not have division. That's okay. There is something we can do instead of division, but we're not going to be covering that this semester. Really just addition, subtraction, and multiplication. So let's create a few matrices. Say I've got a matrix A. It's just the numbers 1, 2, 3, and 4. We would say that that matrix is a 2 by 2 matrix because it has 2 rows and 2 columns. Say we've got a matrix B, which is 0, 1, 2, and -1. Also a 2 by 2 matrix. It has 2 rows and 2 columns. And then let's say we've got a matrix C, 2, 1, 4, 0, 1, -7. That would be a 2 by 3 matrix because it has 2 rows and. All right, so let's talk about adding real quick. Adding 2 matrices. If I made you guess how to do it, you would probably guess how to do it correctly. It is not super unintuitive. To add 2 matrices, we're just going to add the corresponding elements. Add the 1 and the 0 to get 1. Add the 2 and the 1 to get 3. Add the 3 and the 2 to get 5. And then add 4 and -1 to get 3. Not too bad. Some of the ones that the homework gives you are easier to do in your head than in the calculator, though you can use the calculator for these. There are some in the homework, however, that use variables. So for example, maybe it says 1, 2, 3, 4, maybe that's an X instead of a 0. Well, then we would say, okay, I need 1 plus something, gives me 1. What has to be that something? That would be 0, right? So there are some of these that you do need to know how to add by hand, so that you can solve the ones of these in use variables. Yeah.
So when they do use variables, they will give us a solution matrix. So we can
Yes,
cross
yeah,
reference it.
right, exactly. So they might write, 1 equals, and they might make it tricky. They'll do, 1 plus X plus 1 equals 1, right? And so you just kind of have to, you could just write 1 plus X plus 1 equals 1, and you can just solve. That's the basic idea. Subtraction works the same way, so I'm not going to do a subtraction example. You just subtract the corresponding elements. Well, let's try to add A plus C. Those don't look the same. As I mentioned, when we add matrices, we add corresponding elements. Well, my 1, 2, 3, and 4 have corresponding elements, but my 4 and -7 do not have corresponding. Right? So what do we do in this case? Well, no. We can't do it. To add, your matrices must be the same size. Or subtract. Add or subtract, matrices must be the same size, meaning 2 by 3 can be added to a 2 by 3, a 5 by 7 can be added to a 5 by 7, but you can't add a 2 by 2 and a 2. Any questions so far? There's 2 different types of multiplication within matrices. The first one is pretty easy. Let's just say we want to define 2A. So this is called scalar multiplication. You don't need to know that, but it's when you multiply one matrix and one number, as opposed to multiplying 2 matrices together. And all we have to do here is take 2 and multiply it times our matrix. This is another one of those. If I asked you to guess how to do it, you'd probably guess correctly. We're just going to distribute that 2 times every element in our matrix. 2, 4, 6, 7. Matrix multiplication, on the other hand, is not intuitive whatsoever. If I asked you to guess how to do it, you would almost certainly not guess correctly, and that's okay. I would not have either before I learned how to do it. Well, let's multiply A times B. So that was 1, 2, 3, 4. Matrix A. Matrix B was 0, 1, 2, -1. Now, I'm going to multiply this first one by hand for a couple reasons, because there's a couple points I want to make that aren't as helpful if I do it on the calculator. You will be able to use the calculator. You will not at any point during the semester need to know how to multiply matrices by hand. You do need to know how to add them by hand because we have those ones where there's variables. You do not have to know how to multiply them. So I'm going to go through this process. If it doesn't make a ton of sense, that's okay. Hopefully you can at least get enough out of it to understand my couple of points that I want to make here. So to multiply 2 matrices, we multiply the rows of one matrix times the columns of the other. So to multiply matrix A times B, we're going to multiply the first row of A times the second column of B. And the way we do that is we multiply 1 times 0. And then we multiply 2 times 2. We add those together. All of that gives us our top left element. You don't necessarily have to write this down if you don't want to. You're welcome to. Again, I'm not going to ask you to do this. All right. Second thing, we'll multiply the first row of A times the second column of B. That's going to be 1 times 1, and then 2 times negative. Multiply the first row of A times both columns of B. Now I'm going to multiply the second row of A times the 2 columns of B. 3 times 0 and 4 times 2. And then 3 times 1 and 4 times negative. Again, what I did there, took a row, and I multiplied it by both rows. Moved my second row, and I multiplied it by both columns. So, we did it. Let's go ahead and simplify that to get our answer. So we got 0 plus 4. Top left one is 4. Top right, I've got 1 plus -2, which gives us -1. Bottom left, I've got 0 plus 8. And then bottom right, I've got 3 plus -4. That's going to give me another 7. -4. That's what we get when I multiply A times B. Now, we're not going to do all of this next one. Let's look at what happens if we multiply B times A. Same 2 matrices, and we're wanting to multiply them together. So, very first step, we'll multiply the first row of B times the first column of A. That's going to be 0 times 1 plus 1 times 3. So looking at just that first element, are we going to get the same answer for BA as we got for AB? No. Right? 0 plus 3, we'd have 3 in the top left of that. And that makes sense, right? Because the rows and columns we are multiplying together are not the same. Okay. So the main takeaway here is that with real numbers, the numbers that we're used to, 2 times 5 is the same as 5 times 2, right? We can do that in either order. If you have lots of numbers, we can change the order, that's fine. But here, A times B does not equal B times A. There are a few circumstances in which they can equal one another. For example, if A and B are the same matrix, obviously you can swap the orders, but we don't need to worry about those rules. All right, one more point that I want to make. Let's look at A times C. Yes, you do row by column, exactly. So when we multiply A times C, let's think about if we could do it. So we would be multiplying the rows of A times the columns of C. Are there the same number of things in that row of A as there are in the column of C? There are, right? There's 2 things in that first row and 2 things in that first column. So I can multiply my 1 times 2 and my 2 times 0. And then I can move on and multiply 1, 2 times 1, 1. And I can multiply 1, 2 times 4, -7. And I can keep going if there were more and more columns. But really what needs to happen for this to work is that I need to have the same number of things here as I have here, because those are the things that I need to multiply, right? Because if I wanted to do it in the opposite order, C times A, Do I have the same number of things in my row as in my column? No. So what I need to happen here, A is a 2 by 2, C is a 2 by 3. Here, C is a 2 by 3, A is a 2 by 2. I need these two numbers to match.
Two outside numbers are the dimensions of the page.
Yeah, that's exactly right. The two outside dimensions would be the solution. So here, we cannot multiply those because these two things are not equal, right? So basically what needs to happen is the number of rows of this one needs to equal the number of rows. C needs to equal the number of columns here. No, other way. Sorry, wrote that wrong. Number of columns here needs to equal the number of rows here. As long as that is true, then we can multiply our matrices. All right, so again, numbers 1 through 35, I would recommend doing those before next Tuesday. Please feel free to email me questions. In the meantime, I do have office hours this afternoon. You can find those in the email that I sent out. Make sure to have a clicker by next Tuesday. Start using on Tuesday. See you all next week.